Okay, and then we picked our dates, so make sure you got that marked. Saturday, March 1st, 4 p.m. is our little lab experiment. And if you would, please bring a clean 2-liter pop bottle with a screw cap. And I'll post that on Blackboard, the map, and all that stuff. All right, energy coupled reactions. So it's possible to drive an endergonic reaction with an exergonic reaction. So we're going to drive one reaction with the other. What's important is that the overall free energy change has to be negative. And if it is, it'll be spontaneous. Clarify that as the important pathway. Okay, so we're going to see cases where we have more than one step. So we're going to go A to B to C to D, where my free energy change for one, maybe the first one is a negative 15 kilojoules per mole, and for the second one, it might be a positive 18 kilojoules per mole. And then the last step might be a negative 5 kilojoules per mole. Okay. So the first step is spontaneous, the last step is spontaneous, but the middle step isn't. But if you add all those up, overall, my negative 15 plus my 18 minus my 5 is a what?
2.
Negative 2 kilojoules per mole. So overall, the pathway is spontaneous. And moves towards D. So cells are going to use high energy compounds in order to couple reactions together. And our favorite high energy compound is ATP. What does that stand for? I think I heard it. I heard it right last night. Yep.
Is it just as common to see GTP in others?
Sure.
Or it is?
Yeah, this is our favorite. Yeah.
So, like, most reactions we say that it takes like 2 ATP, it could also take 2 GTP.
No, they're reaction specific.
Okay.
So something that uses ATP to drive a reaction is probably specific just for ATP. But we will see reactions where something else is used, and the second most common one is GTP.
Well, because I know that silver's like when I took one of those classes, like if GTP is made in the Krebs cycle,
Yes.
but he just has it as ATP, like he just switched them like that.
Because they're equivalent, and the reason is because ATP is used to synthesize GTP.
Okay.
Now, in that particular step, GTP is what's being made,
Yes.
but in the cell in general, ATP can be converted to any of the others.
Okay.
Yeah. So it's an ATP equivalent, and we will call it that. And later when we're adding up all the ATP, we'll add it up as ATP equivalents. Yeah, but yeah, this works whether it's a GTP, a CTP, a UTP, a TTP. They're all high energy compounds. Okay, so you did a couple of these on the homework. So ATP plus water actually has multiple possible outcomes. One of which, and is probably the most common, is you just hydrolyze off the terminal phosphate, and so we get a DP, the diphosphate, plus an inorganic phosphate. And the standard free energy change for that is one that you should know by heart, but I'm going to give you a table on the exam, so if you don't know it by heart, I guess it's not the end of the world. Negative 30.5 kilojoules per mole. Okay. EDP can also be hydrolyzed by water, in which case what will I get?
AMP?
AMP plus
PPI.
PI.
PI, yeah. So if I start
yeah.
with ADP and hydrolyze it down to AMP, then it's also going to be just AMP plus 1 PI. That one is not in your table in the book because it's not a very common reaction physiologically. You don't see it very often. So yeah, you can hydrolyze ADP down to AMP. Yes, you get a decent amount of energy released, but it's not as physiologically relevant. Okay, instead, what your book shows you is ATP plus water going to AMP, and then what do you get?
PPI.
PPI. Or this is called pyrophosphate. That one you will see more often than hydrolysis of ADP. And the free energy change for that one is even better, so negative 45.6 kilojoules per mole. And the other one that is again very physiologically relevant is hydrolysis of the pyrophosphate. And frequently you'll see this reaction also coupled with that reaction where both of them happen in sequence. So if I add water to the pyrophosphate, what do I get?
2 PI.
2 PI. So 2 inorganic phosphates, and that standard free energy change is another negative 19.2 kilojoules per mole. So sometimes you'll see ATP down to AMP, and where this is not enough to drive an inorganic process, but as soon as the pyrophosphate is hydrolyzed, it is. So we'll see examples like that later on. So why is ATP high energy? Your book gave you some different reasons. Why is ATP high energy?
Resonance.
Resonance. We have competing resonance structures. Or the electrons in the phosphoanhydride bonds. What was another reason? Remember? I showed the picture later. Okay. So all of these are high energy. The phosphoanhydride bond. This phosphoanhydride bond is high energy, phosphoanhydride bond is high energy. When we're talking about hydrolysis, we have a nucleophile coming in, and any of these phosphorus are potentially an electrophilic site that could attack. So water could attack here, or it could attack there, or it could attack here. Here they're showing you the competing resonance structures. So I've got electrons that can come over here, and then they pop up onto oxygen, or go the other way. And so I'm seeing electrons being pulled in two different directions in those resonance structures. And then the other thing that's going on is what they're trying to show right here. What does that represent? Not a bond.
Oh.
Negative charges repel each other.
Negative charges repel each other. Yeah. So we have electron repulsion between neighboring oxygens. And they did give a third reason, which you may have just read over from this. But the hydrolysis products have a lower solvation energy. Oh, I just said that backwards. Sorry. Ah!
Oh.
I know, I'm so sorry. I just said it backwards. Okay. We go. ATP has a lower solvation energy than the hydrolysis products. And what this means is solvation energy is kind of a measured energy released when water solvates a particular species. So solvation energy equals energy released upon solvation. And basically you can think of it as is less of an energy cost to solvate something small than big, and it's all related to entropy. So if you have a little molecule, I don't know what it is, something like that, water has to build a cage, and I don't even want to draw out all those little molecules, so we'll just draw out a little version thing. So there's a little water cage, because water wants a hydrogen bond with itself, and it'll hydrogen bond to things that also have polar groups on it. But water has to build this cage around the molecule, and the bigger the molecule, the bigger the cage, and there's an entropy cost there. And so it's much easier to solvate little things, because you only have to build a little cage, than it is to solvate something that's very big. And so that's also something that contributes to ATP wanting to be hydrolyzed, wanting to be broken down into smaller species. Okay, so ATP is high energy. We're going to couple hydrolysis with some other reactions. So we're doing an example of an ATP coupled reaction. So we just said that ATP plus water could be hydrolyzed to ADP plus an inorganic phosphate. And we said that the free energy change is equal to negative 30.5 kilojoules per mole. Okay, here's a reaction that we're going to look at really soon in the next chapter. So inorganic phosphate plus a glucose could make a glucose 6-phosphate. And I'm just gonna write the phosphate as a P, so glucose 6P. So that just means the phosphate group's attached to the hydroxyl on the number 6 carbon of glucose. Plus a water, we get a water there, and that free energy change is a positive 13.8 kilojoules per mole. Okay, if I add those two processes together, and then cancel what shows up on both sides, so water shows up on both sides, and inorganic phosphate shows up on both sides, then I get ATP plus glucose going to glucose 6P plus ADP. And then I just add the energies. So my standard free energy change for this is the negative 30.5 plus the 13.8, which is a negative 16.7 kilojoules per mole. So you have a spontaneous process coupled to a non-spontaneous process so that the overall coupled reactions is spontaneous. But this isn't what happens in the cell. So here it's shown as two separate steps that, yeah, we added together to couple them together. But it doesn't happen in two separate steps where that is released and then this is absorbed. Instead, the reactions are enzyme catalyzed and it ends up being a phosphoryl transfer rather than a hydrolysis that occurs. And then the ligation of them together. So first thing to note is that ATP hydrolysis is thermodynamically favored. But kinetically disfavored. What does that mean? If something is thermodynamically favored, what does that mean? Has a negative delta G, yeah. So it's thermodynamically favored. We saw that it has a negative 30.5 kilojoules per mole for delta G. So it's spontaneous. It's thermodynamically favored. It's kinetically disfavored. What does that mean?
The rate is slow.
Really slow. Really darn slow. Okay, so the gen chem example that's usually given is diamonds, right? That diamonds are currently decomposing into carbon. That is a spontaneous process. I can't stop it. It's going to happen. But it's really slow. So, for my lifetime, I'm not going to worry about the diamonds, and probably not for the next several generations. I'm not going to worry about it. Probably for thousands of years, nobody's going to worry about it because it's really slow. So, if we had a process in the cell where we needed to couple these two reactions together, the cell cannot wait for ATP just to hydrolyze itself because it's not going to happen, not on a time scale that's useful. Okay, so it has to be, because of this, it has to be enzyme catalyzed. To couple these processes. So hydrolysis and phosphorylation are combined into one phosphoryl transfer step. And this is catalyzed by what kind of enzyme?
hydrolase.
Oh, not a hydrolase. Hydrolase is the reverse process. So if I'm taking phosphate from ATP and putting it on
Kinase?
something else, it's a kinase. There we go. The hydrolase is the phosphatase, and that's where we cut it off. Okay, so kinases are going to do phosphoryl transfers. And then when we write this coupled reaction, it is actually going to look like this. I got glucose going into glucose 6-phosphate. And we're not drawing things out now because we're going to in the next chapter. We're going to draw them out. And then you've got some ATP coming in and some ADP leaving. And this whole thing is catalyzed by a kinase. And particular kinase is called hexokinase. And the standard delta G of that is negative 16.7 kilojoules per mole. That value is the same because it is pathway independent. You might remember that again from Gen Chem with free energy changes for reactions when you have a series of reactions, as opposed to some one step that gives you the same product. It is what you start with and what you end with that matter. It doesn't matter what the steps are in between. The free energy changes can be the same, regardless of the pathway. Other phosphorylated compounds can also act as these energy transfer molecules. And there's a table in your book that you're going to want to get familiar with. And actually, I'm not sure it's still 13.2 because I didn't update this when we looked at it. But there's a table that has free energy changes for hydrolysis of phosphate groups off of different compounds. And so we looked at ATP going to AMP, there's the negative 45.6, ATP going to ADP, there's the negative 30.5. Here's the pyrophosphate, hydrolysis pyrophosphate, negative 19.2. But then there's some other things on here as well. So the phosphoenol pyruvate went through this phosphoglycerate, single phosphate, phosphocreatine. So there are a bunch of other phosphorylated compounds. And hydrolysis of that phosphate group, when we remove the phosphate group, we get different amounts of energy released, but it is always negative for all of these. So these are all spontaneous processes, which means they can all be coupled to some other reaction. This table here is kind of showing you that you can always go from a higher energy to a lower energy. You can't go back the other way, because if you go back the other way, then you get a positive energy change. So phosphoenol pyruvate, for example, if we hydrolyze off its phosphate group, we can stick its phosphate group onto anything underneath it in the table. And it still will be an overall negative free energy change. Okay, so we'll see if you understood that. So will this energy coupled reaction be spontaneous? And we have fructose 6-phosphate plus glucose goes to a glucose 1-phosphate to fructose. And remember that these energies represent hydrolysis of a phosphate off of a group. spontaneous the way it's written. Fructose 6-phosphate, when we're down here, if we remove the phosphate group, we're going to reduce 13.8 kilojoules per mole. Glucose is getting the phosphate group. And we aren't showing phosphorylation energy, so we're only showing hydrolysis. So if you want the phosphorylation energy, you have to flip the sign in order to get it. So glucose 1-phosphate, which is our product, if we remove the phosphate group from that, we release 20.9, which means if we add a phosphate to the glucose, it's a positive 20.9. So positive 20.9 plus a negative 13.8 is positive overall, which means that as written, this is not spontaneous. Is the reverse reaction spontaneous?
Yes.
Yeah, so I can go the other way, I can go backwards. Then that would be spontaneous. Yep.
The table number is 14.3.
14.3. The other good news is that I will also give that table to you on the exam, so that you have all the energies.
The number you gave in here for the glucose 6-phosphate was 16.7. What's the difference between the glucose 6-phosphate there being 13.8?
It's a 1-phosphate, not a 6.
No, there's a glucose 6 down below as well.
It's the, what did I do? No, it's the net is, so for, if you just add a phosphate group to the 6th position, it's a 13.8. If you couple it with ATP,
Okay.
then your net
Is the negative 16.
is the negative 16. Okay, we're gonna do another one. Example, phosphocreatine. Okay, you took physiology, so you know what that does. You might know what it does. What does it do? Yeah, it can store ATP in muscles. And it doesn't literally store the ATP, it just stores the energy down in ATP. So ATP plus creatine. I can move that phosphate group over to make the phospho creatine plus ADP. Okay, if you wanted, you could write the ATP or the ADP over the arrow, and that would be fine. And there's an enzyme that does this called creatine kinase. Okay. If we look at our table, ADP, or ATP going to ADP, releases the 30.5. Phosphocreatine, if you remove the phosphate group, is a negative 43.1, but if you're adding a phosphate group, it's a positive 43.1. So is that a spontaneous process?
No.
No.
No. And yet it happens. So that's the, let me look at my chart here. So the ATP hydrolysis is equal to a negative 30.5 kilojoules per mole. And phosphorylation, the creatine, is a positive 43.1 kilojoules per mole. So I flipped the sign because I'm talking about putting phosphate on it as opposed to taking it off. And so coupled, I get a, what is that? Oh, it's a positive 12.6. Does that sound right?
Yeah.
And just a reminder that this is equal to standard free energy change, because those energies in the table are standard free energies. So this implies that it takes energy. I'm going to consume energy in order to be able to store my ATP. But in reality, in a cell, this is a near equilibrium process. Which means that my actual free energy change is equal to approximately what? Zero. Okay. Which is why we can actually do this. So in your muscles, you don't need the ATP right away. It stores it as phosphocreatine, and then later when you've depleted all of your ATP stores in your muscles, it will pull the ATP back out, and that's that equilibrium process and go very quickly in either direction, just based on concentrations available. So this is an example where you have to be careful about making assumptions based off standard free energy changes, because the concentrations in the cells are not 1 molar. They're not 1 molar. And for the most part, we're going to be able to rely on the standard free energy changes, but every once in a while we can't, and I will point those out when we see them. Bioesters. These are also high energy molecules. So we see these as energy transfer molecules as well, and you can couple these to endogenic reactions. So with your bioester, you got something that looks like that. The ester in the phosphate, because ATP also has more than phosphoester bond, it's not as high energy. The bioester is higher energy, and I was going to try to look up why before coming, and I forgot. And your book doesn't go through as detailed an explanation as to why. They just say it's high energy, so trust it. It is. So if you hydrolyze this and you measure how much energy is given off, what was it? 7.4. There we go. The free energy change for hydrolysis. Just an example of an acetyl coenzyme A, which is one we're going to see in the future, is equal to a negative 31.5 kilojoules per mole, which is comparable to hydrolysis of ATP. Coenzyme A, we'll look at the structure. It's not a structure you need to know. We're going to abbreviate it a lot. So this is just a capital C, little a, capital A. And coenzyme A has a thiol group on it that can be put into an ester. And so this would be the acetyl ester. And then if we add water to that, we get the coenzyme A. And sometimes, and you just have to be aware of this, sometimes the book, once that ester linkage is broken, they just write coenzyme A. Sometimes they want to show what functional group is important, and they'll add the little SH. But whether they put the SH there or not, it just depends on what they're trying to demonstrate, and you should know that coenzyme A always has a thiol group on it. Okay. Plus the acetic acid. And then that's that negative 31.5 kilojoules per mole. Okay, so this is why we're not going to learn the structure for coenzyme A. We got lots of other stuff to memorize, so this is one that we won't worry about. We will always use the abbreviation, but it is something that we're going to see over and over again in different reactions. So we've got something that looks like a nucleotide here with some phosphate groups on it, and then you've got this funky bridging thing, and then another little group that looks very amino acid-like, and then you have this little bioester linkage, and so that's the acetyl group that was frequently added when we did. And so in particular, when we're looking at fatty acid metabolism, there's going to be a lot of transfer of cell groups going on back and forth from the cellulose. Okay, so typically we're going to see phosphates being moved around in order to move energy around, or we might see formation of bioesters to help move energy around. But the other way to move energy around is with electrons. So organisms must have some kind of fuel. To create high energy compounds like ATP. And this energy comes from basically redox reactions. So carbon fuels are oxidized and then electron transfers enable synthesis of ATP. And like I said before, ATP is used to make GTP, CTP, ATP, all those other triphosphates. Okay, this requires electron carrier molecules. That you will need to know. So NAD, plus, and in parentheses I'll say or NADP, but we only see NADP in certain situations, so for the most part we're going to ignore that one. Mostly it'll just be NAD. And then the other one to know is FAD, and that one does not have a positive charge in it. Okay, NAD is a hydride acceptor. And FAD is either a hydride, right, I shouldn't say hydride, I should say hydrogen, meaning H2 acceptor, or single electron acceptor. So it can, NAD only works in pairs of electrons, but FAD can transfer one at a time. What's a hydride? I got a hydrogen with what on it?
Negative.
Negative charge, because it has two electrons. So NAD plus, and I'm just going to write it like this for now, as a hydride coming in, makes NADH. If I am accepting electrons and getting reduced, then I am an oxidizing agent. If I already have the electrons and I can give them up, because I could go back the other way, then I am a reducing agent. FAD, and we'll show hydrogen coming in. reducing agent. These are also structures you do not have to drop. We'll just deal in abbreviations. There's my NAD. So something that starts out looking like an ADP, and then I'm going to add this other regular sugar and this independent group. And right now it's being shown in the oxidized form. So oxidized form, and then I can accept that hydride to make a reduced form, and that is reversible. And the difference, that P is just stands for a phosphate. There's a phosphate group off of that ring. And then FAD, again, something that starts off looking like ADP, and then I have this big riboflavin group attached to it. This is where interesting things can happen because I have this conjugated system down here where I can accept either one or two electrons. So I accept one, that radical is stabilized by resonance across all the rings here. So that's why I can take just one electron at a time. And then if it takes the second one, there is in this fully reduced form, the H2. Mostly we won't see single electron transfers until we get to the electron transport chain, and then we'll see them there. Okay, so in the time we have left, we need to do a little review or a redox. So we're going to oxidize fuel. So we're going to oxidize glucose. So C6, H12, O6 is glucose. And if we add oxygen to that, we can make carbon dioxide plus water. Okay, is that balanced?
No.
No. Can I just slap some coefficients on there and call it good?
No.
No, because this is a redox reaction, which means you have to balance half reactions and assume that the coefficients you put on it are correct. Okay. Now, as it turns out, this one you can just slap some coefficients on it and it works, but that isn't always the case. So, this is your next question. You have that written down so far? I want to know how many electrons total are transferred in the balanced reaction for oxidation of glucose to carbon dioxide, and I'll wait to start that going. But one of those is the right answer. So you need to split that apart into an oxidation half reaction and a reduction half reaction, and you have to balance. And do you remember what you balance? How do you balance oxygen and hydrogen? To balance hydrogen, what do I add? Let's start with the other one. To balance oxygen, what do I add? Okay. Balance hydrogen, you add protons, right? To balance oxygen, you add water. Remember doing that? Give it a try, and then we'll write it out. Yeah, Gen Chem, all Gen Chem stuff.
Do we learn this again?
Yes, we did.
Really?
I don't remember it.
click something so I know you hear. Okay. 24 is correct.
24?
Oh, 24. 24 is
Ouch.
Oh.
Oh, so now, okay. 24 is correct. So split this into your two half reactions. So in this case, oxygen is getting reduced to water. Glucose is getting oxidized to carbon dioxide. And if you don't remember which is which, this is your Leo-Gosker that you use to figure that out. Or, gain of oxygen, or is an oxidation usually, gain of hydrogen is a reduction usually. Okay, so I'm not balanced here at all. So I have two oxygens here, I have two hydrogens and an oxygen there. The order does make a difference. You start with non-carbon atoms, and then after that you usually worry about the oxygens. So if I want to have the right number of oxygens, what do I need to do over here?
2.
Multiply by 2. Okay, now I have 4 hydrogens. There are no hydrogens over here, so how do I add them?
Plus.
Protons. So I'm going to have 4 protons that I add to that. Okay. Charges also have to balance. So if there's no charge over here, but I have 4 positives, I need to add 4, sorry, that's crowded, 4 electrons to balance. Okay, now I'm going to come down here, and you start with non-carbons, or sorry, non-oxygen hydrogen atoms. So I start with carbon, so I need to multiply that by
6.
6. Okay, moving on to water. I have 6 oxygens here and 12 there, so what do I need to add over here?
6 more.
6 what?
Waters.
Waters. Okay, so I add my 6 waters. Now I've got a whole bunch of hydrogens over here. I've got 12, I've got 24, so how many hydrogens over here?
24.
24 added as protons. Then I have to make the charges balance, so what do I also add?
Electrons.
And they have to be 24 electrons. Now, the electrons moving from one side to the other of my redox reaction have to match. And I only have 4 here and I have 24 there. So what do I need to do this whole thing?
6.
Times 6.
Multiply by 6 to get the whole thing to balance. And so then when you're all done, you've multiplied this all through, all of those protons will cancel, all of the electrons are going to cancel, and I'm going to end up with just the coefficients, which is the 6O2 plus C6H12O6 goes to 6 carbon dioxide plus 6 waters. But unless you go through the half reaction treatment, you don't immediately know how many electrons are being moved around in that case. And it's going to be important to us to know how many electrons are being moved. Which is 24.
Why is it not 12 waters on top of single
Because I've got water on both sides, and they're going to cancel.
Oh, right. Okay.
Yeah, waters will cancel. Okay, so we will pick up there with a whole bunch of redox examples next time.
Good to know.